Hello. In the first section, we start with the core concepts. We look at the cluster architecture at a high level and then look at some of the API primitives, such as the basic concepts like pods, replica sets, deployments, followed by services. If you have attended the beginner's course or other certification course for application developers, then you might want to skip some of these topics, or maybe just go through the practice tests alone. We will now start with the cluster architecture. Hello and welcome to this lecture. We start with a basic overview of the Kubernetes cluster architecture. We first look at the architecture at a high level, and then we drill down into each of these components. We see what their roles and responsibilities are and how they are configured. And finally, you go through a practice test where you look at an existing cluster and are asked to identify various details with respect to these components in the cluster. We're going to use an analogy of ships to understand the architecture of Kubernetes. The purpose of Kubernetes is to host your applications in the form of containers in an automated fashion so that you can easily deploy as many instances of your application as required and easily enable communication between different services within your application. So there are many things involved that work together to make this possible. So let's take a 10,000 feet look at the Kubernetes architecture. We have two kinds of ships in this example. Cargo ships that does the actual work of carrying containers across the sea, and control ships that are responsible for monitoring and managing the cargo ships. The Kubernetes cluster consists of a set of nodes, which may be physical or virtual, on-premise or on cloud, that host applications in the form of containers. These relate to the cargo ships in this analogy. The worker nodes in the cluster are ships that can load containers. But somebody needs to load the containers on the ships. And not just load, plan how to load, identify the right ships, store information about the ships, monitor and track the location of containers on the ships, manage the whole loading process, etc. This is done by the control ships that host different offices and departments, monitoring equipments, communication equipments, cranes for moving containers between ships, etc. The control ships relate to the master node in the Kubernetes cluster. The master node is responsible for managing the Kubernetes cluster, storing information regarding the different nodes, planning which containers goes where, monitoring the nodes and containers on them, etc. The master node does all of these using a set of components together known as the control plane components. We will look at each of these components now. Now, there are many containers being loaded and unloaded from the ships on a daily basis. And so you need to maintain information about the different ships, what container is on which ship, and what time it was loaded, etc. All of these are stored in a highly available key value store known as etcd. etcd is a database that stores information in a key value format. We will look more into what etcd cluster actually is, what data is stored in it, and how it stores the data in one of the upcoming lectures. When ships arrive, you load containers on them using cranes. The cranes identify the containers that need to be placed on ships. It identifies the right ship based on its size, its capacity, the number of containers already on the ship, and any other conditions such as the destination of the ship, the type of containers it is allowed to carry, etc. So those are schedulers in a Kubernetes cluster. A scheduler identifies the right node to place a container on based on the container's resource requirements, the worker node's capacity, or any other policies or constraints, such as taints and tolerations or node affinity rules that are on them. We will look at these in much more detail with examples and practice tests later in this course. We have a whole section on scheduling alone. There are different offices in the dock that are assigned to special tasks or departments. For example, the operations team takes care of ship handling, traffic control, etc. They deal with issues related to damages, the routes the different ships take, etc. The cargo team takes care of containers. When containers are damaged or destroyed, they make sure new containers are made available. You have the services office that takes care of the IT and communications between different ships. Similarly, in Kubernetes, we have controllers available that take care of different areas. The node controller takes care of nodes. They're responsible for onboarding new nodes to the cluster, handling situations where nodes become unavailable or gets destroyed. And the replication controller ensures that the desired number of containers are running at all times in a replication group. So we have seen different components like the different offices, the different ships, the data store, the cranes. But how do these communicate with each other? How does one office reach the other office, and who manages them all at a high level? The Kube API server is the primary management component of Kubernetes. The Kube API server is responsible for orchestrating all operations within the cluster. It exposes the Kubernetes API, which is used by external users to perform management operations on the cluster, as well as the various controllers to monitor the state of the cluster and make necessary changes as required, and by the worker nodes to communicate with the server. Now, we're working with containers here. Containers are everywhere, so we need everything to be container compatible. Our applications are in the form of containers. The different components that form the entire management system on the master node could be hosted in the form of containers. The DNS service, networking solution can all be deployed in the form of containers. So we need the software that can run containers, and that's the container runtime engine, a popular one being Docker. So we need Docker or its supported equivalent installed on all the nodes in the cluster, including the master nodes, if you wish to host the control plane components as containers. Now, it doesn't always have to be Docker. Kubernetes supports other runtime engines as well, like Containerd or Rocket. Let us now turn our focus onto the cargo ships. Now, every ship has a captain. The captain is responsible for managing all activities on these ships. The captain is responsible for liaising with the master ships, starting with letting the master ship know that they are interested in joining the group, receiving information about the containers to be loaded on the ship, and loading the appropriate containers as required, sending reports back to the master about the status of this ship and the status of the containers on the ship, etc. Now, the captain of the ship is the kubelet in Kubernetes. A kubelet is an agent that runs on each node in a cluster. It listens for instructions from the Kube API server and deploys or destroys containers on the nodes as required. The Kube API server periodically fetches status reports from the kubelet to monitor the status of nodes and containers on them. The kubelet was more of a captain on the ship that manages containers on the ship, but the applications running on the worker nodes need to be able to communicate with each other. For example, you might have a web server running in one container on one of the nodes and a database server running on another container on another node. How would the web server reach the database server on the other node? Communication between worker nodes are enabled by another component that runs on the worker node known as the kube proxy service. The kube proxy service ensures that the necessary rules are in place on the worker nodes to allow the containers running on them to reach each other. So, to summarize, we have master and worker nodes. On the master, we have the etcd cluster, which stores information about the cluster. We have the kube scheduler that is responsible for scheduling applications or containers on nodes. We have different controllers that take care of different functions, like the node controller, replication controller, etc. We have the Kube API server that is responsible for orchestrating all operations within the cluster. On the worker node, we have the kubelet that listens for instructions from the Kube API server and manages containers, and the kube proxy that helps in enabling communication between services within the cluster. So that's a high-level overview of the various components. We will drill down into each of these in the upcoming lectures. That's it for now, and I will see you in the next lecture.
So you're going to come across Docker and Containerd many times going forward. So when you read older blogs or documentation pages, you'll see Docker mentioned along with Kubernetes. And when you read newer blogs, you will see Containerd, and you'll wonder what the difference is between the two. And there are a few CLI tools like CTR, cry control, or node control. And you'll wonder what are these CLI tools and which one should you be using. So that's what I'm going to explain in this video. So let's go back in time to the beginning of the container era. And in the beginning, there was just Docker, and there were other tools like Rocket, but Docker's user experience made working with containers super simple, and hence Docker became the most dominant container tool. And then came Kubernetes to orchestrate Docker. So Kubernetes was built to orchestrate Docker specifically in the beginning. So Docker and Kubernetes were tightly coupled. And back then, Kubernetes only worked with Docker and didn't support any other container solutions. And then Kubernetes grew in popularity as a container orchestrator. And now other container runtimes like Rocket wanted in. So Kubernetes users needed it to work with container runtimes that are other than just Docker. And so Kubernetes introduced an interface called Container Runtime Interface, or CRI. So CRI allowed any vendor to work as a container runtime for Kubernetes as long as they adhere to the OCI standards. So OCI stands for Open Container Initiative, and it consists of an image spec and a runtime spec. Image spec means the specifications on how an image should be built. So that's what it defined. An image spec defined the specifications on how an image should be built. And the runtime spec defined the standards on how any container runtime should be developed. So keeping these standards in mind, anyone can build a container runtime that can be used by anybody to work with Kubernetes. So that was the idea. So Rocket and other container runtimes that adhere to the OCI standards were now supported as container runtimes for Kubernetes via the CRI. However, Docker wasn't built to support the CRI standards. Because remember, Docker was built way before CRI was introduced, and Docker still was the dominant container tool used by most. So Kubernetes had to continue to support Docker as well. And so Kubernetes introduced what is known as Docker shim, which was a hacky but temporary way to continue to support Docker outside of the container runtime interface. So while most other container runtimes worked through the CRI, Docker continued to work without it. So now you see, Docker isn't just a container runtime alone. Docker consists of multiple tools that are put together. For example, the Docker CLI, the Docker API, the build tools that help in building images. There was support for volumes, auth, security, and finally, also the container runtime called runc, and the daemon that managed runc, and that was called as containerd. So containerd is CRI compatible and can work directly with Kubernetes as all other runtimes. So containerd can be used as a runtime on its own, separate from Docker. So now you have containerd as a separate runtime and Docker separately. So Kubernetes continued to maintain support for Docker engine directly. However, having to maintain the Docker shim was an unnecessary effort and added complications. So it was decided in version 1.24 release of Kubernetes to remove Docker shim completely, and so support for Docker was removed. But you see, all the images that were built before Docker was removed, so all the Docker images continue to work because Docker followed the image spec from the OCI standard. So all the images built by Docker follow the standard. So they continue to work with containerd, but Docker itself was removed as a supported runtime from Kubernetes. So that's kind of the whole story. And now let's look into containerd more specifically. So containerd, although is part of Docker, is a separate project on its own now and is a member of CNCF with the graduated status. So you can now install containerd on its own without having to install Docker itself. So if you don't really need Docker's other features, you could ideally just install containerd alone. So typically we ran containers using the docker run command when we had Docker. And if Docker isn't installed, then how do you run containers with just containerd? Now, once you install containerd, it comes with a command line tool called CTR, and this tool is solely made for debugging containerd and is not very user friendly as it only supports a limited set of features, and this is what you can see in the documentation pages for this particular tool. So for the other than the limited set of features that it provides, any other way that you want to interact with containerd, you'll have to rely on making API calls directly, which is not the most user-friendly way for us to operate. So just to give you an idea, the CTR command can be used to perform basic container related activities such as pull images. For example, to pull Redis image, you would run the CTR images pull command followed by the address of the image. And to run a container, we use the CTR run command and specify the image address. But as I mentioned, this tool is solely made for debugging containerd and is not very user friendly and not to be used for running or managing containers on a production environment. So a better alternative recommended is the nerd control tool or nerdctl tool. So the nerd control tool is a command line tool that's very similar to Docker. So it's like a Docker-like CLI for containerd. It kind of supports all or most of the options that Docker supports. And apart from that, it has the added benefit that it can give us access to the newest features implemented into containerd. So for example, we can work with the encrypted container images, a rather new feature that will eventually be implemented into the regular Docker commands in the future. It also supports lazy pulling of images, P2P image distribution, image signing and verifying and namespaces in Kubernetes, which is not available in Docker. So the nerd control tool works very similar to Docker CLI. So instead of Docker, you would ideally simply have to replace it with nerd control. So you can run almost all Docker commands that interact with containers like this. So some examples are, instead of running the Docker run command to create a container, to run a container, you could just use the nerd control run command. And similarly, let's say you want to use some options for port mappings or exposing ports with the -p option for the Docker run command. You could do the same with nerd control, simply replace Docker with nerd control. So that's pretty easy and straightforward. So now that we have talked about CTR and the nerd control tool, it's important to talk about another command line utility known as CRI-CTL or CRI control. So earlier we talked about the container runtime interface or CRI, which is a single interface used to connect CRI compatible container runtimes like containerd, Rocket, and others. So the CRI control is a command line utility that is used to interact with the CRI compatible container runtime. So this is kind of an interaction from the Kubernetes perspective. So this tool is kind of maintained by developed and maintained by the Kubernetes community, and this tool works across all the different container runtimes. As opposed to earlier, you had the CTR and the nerd control tool that were built by the containerd community specifically for containerd. This particular tool is from the Kubernetes perspective that works across different container runtimes. So it must be installed separately, and it is used to inspect and debug container runtime. So this again is not ideally used to create containers, unlike Docker or the nerd control utility. This is again a debugging tool. You can technically create containers with the CRI control utility, but it's not easy. It's only to be used for some special debugging purposes. And remember that it kind of works along with the kubelet. So we know that the kubelet is responsible for ensuring that the specific number of containers or pods are available on node at a time. So if you kind of go through the CRI control utility and try and create containers with it, then eventually kubelet is going to delete them because the kubelet is unaware of some of those containers or pods that are created outside of its knowledge. So anything that it sees is going to go and delete it. So because of those things, remember that the CRI control utility is only used for debugging purposes and getting into containers and all of that. So let's look at some of the command line examples. So you simply run the CRI control CRI-CTL command for this, and this can be used to perform basic container related activities such as pull images or list existing images, list containers, very similar to the Docker command where you use the ps command. So in Docker you would run the ps command, here you would run the CRI control ps command. And to run a command inside a container in Docker, remember we use the exec command, and it's the same here, along with the same options such as the -i and -t, and then you specify the container ID and then the command that needs to be run. To view the logs, again, you use the CRI control logs command, very similar to Docker command. And one major difference is that the cry control command is also aware of pods. So you can list pods by running the cry control pods command. So this wasn't something that Docker was aware of. So while working with Kubernetes in the past, we used Docker commands a lot to troubleshoot containers and view logs, especially on the worker nodes. Now you're going to use the cry control command to do so. So the syntax is a lot similar, so it shouldn't be really hard. So here's a chart that lists the comparison between Docker and the cry control command line tool. So as you can see, a lot of commands such as attach, exec, images, info, inspect, logs, ps, stats, version, etc. work exactly the same way. And some of the commands to create, remove, and start and stop images work similarly too. So a full list of differences can be found in the link given below.
In the previous versions of Kubernetes, prior to version 1.24, the cry control tool connected to runtime endpoints in the following default order as shown on screen. However, with the release of Kubernetes 1.24, a significant change was made. The dockershim.socket point was replaced with cry-dockerd.sock. As a result, the updated default endpoints for the cry control tool were changed. This change was implemented in response to the deprecation of the previous default settings. Now users are encouraged to manually set the endpoint. These changes are documented in the Kubernetes CRY tools GitHub repository, specifically in pull request 869 and issue 868. It's recommended to review these discussions for a more detailed understanding of the changes.
So to summarize, we have the CTR command line utility that comes with Containerd and works with Containerd, which is used for debugging purposes only and has a very limited set of features. So ideally, you wouldn't be using this at all. So you can kind of ignore this. Then we have the nerd control CLI, which is again from the Containerd community, but this is a Docker-like CLI for Containerd used for general purpose to create containers and supports the same or more features than Docker CLI. So this is something that I think we'll be using a lot more going forward. And then we have the cry control utility, which is from the Kubernetes community, mainly used to interact with CRI compatible runtime. So it's not just for Containerd. This can be used for all CRI supported runtimes. Again, this is mainly to be used for debugging purposes. So if you look at the comparisons here, you can see that CTR and cry control are used mainly for debugging purposes, whereas the nerd control is used for general purpose. The CTR and nerd control are from the Containerd community and works with Containerd, whereas cry control is from the Kubernetes community and works across all CRI compatible runtimes. Well, that's all for now. Thank you for listening.
Hello and welcome to this lecture. This is a quick introduction to etcd for beginners. If you already know about etcd, feel free to skip this video and head over to the next video where we discuss about etcd in Kubernetes. We start with a basic introduction to what a key value store is and how it is different from traditional databases, how to quickly get started with etcd, and how to use the client tool to operate etcd. Later in this course, when we cover high availability, we will discuss about what it means to be a distributed system, how etcd works in a cluster mode, what Raft protocol is, and what are the best practices around the number of nodes in an etcd cluster. So what is etcd? It is a distributed, reliable key value store that is simple, secure, and fast. So let's break it up. So what is a key value store? Traditionally, databases have been in a tabular format. You must have heard about SQL or relational databases. They store data in the form of rows and columns. For example, here is a table that stores information regarding few individuals. The row represents each person and the column represents the type of information being stored. Now, say we want to add additional details about these individuals, say for example, salary. So we add an additional column. Doing so impacts the entire table and all of the individuals in them. We then add salary details to this column. However, not all of them are working, so those cells remain empty. We are then required to store grade information, so we add a new column and update the students with their respective grades. Again, only students have grades, so the corresponding fields for adults are empty. Every time a new information needs to be added, the entire table is affected and leads to a lot of empty cells. A key value store stores information in the form of documents or pages. So each individual gets a document and all information about that individual is stored within that file. These files can be in any format or structure, and changes to one file does not affect the others. The working individuals can have their files with salary fields, and the students can have their pages with grades only. You can add additional details to any of these documents without having to update other similar documents. While you could store and retrieve simple key and values, when your data gets complex, you typically end up transacting in data formats like JSON or YAML. It's easy to install and get started with etcd. Download the binary, extract it, and run. Download the relevant binary for your operating system from the GitHub releases pages, extract it, and run the etcd executable. When you run etcd, it starts a service that listens on port 2379 by default. You can then attach any clients to the etcd service to store and retrieve information. A default client that comes with etcd is the etcd control client. The etcd control client is a command line client for etcd. You can use it to store and retrieve key value pairs. To store a key value pair, run the etcd control set key1 command followed by the value 1. This creates an entry in the database with the information. To retrieve the stored data, run the etcd control get key1 command. To view more options, run the etcd control command without any arguments.
You might come across different versions of commands while exploring etcd and related articles online, so it's important to understand the history of etcd releases so you know what changed when. So the first version of etcd, version 0.1, was released in August 2013. The official stable version, version 2.0, was released in February 2015, and this is when the Raft consensus algorithm was redesigned, and it supported more than 10,000 writes per second. And in January 2017, etcd released version 3 with a lot more optimizations and performance improvements. And finally, in November 2018, that's when the etcd project was incubated in CNCF. So what's most important here is to note the change between version 2 and version 3. So version 2 had been used a lot, and with version 3, there were a lot of changes made. So the API versions changed between version 2 and version 3. So that means the etcd commands changed as well. So that's what I'm going to talk about next. So the set and get commands I showed earlier were for version 2 and won't work for version 3. Your etcd command is configured to work with v2 and v3 at the same time. So how do you find out what version etcd is configured to work with? Run the etcd version command, and it should tell you if it's set to v2 or v3. Now in this output, you can see the etcd version itself, which is v3, so that's the first line. However, the API version is 2. So remember that there are two types of versions. So one is the etcd utility itself, and the other is the API that it is configured to work with, which will either be 2 or 3. So this means, in the current state, it means that it's configured to work with v2. And so if you run the etcd command without any options, then it lists all the commands that it supports, and these are for version 2. And note that with newer versions of etcd, the default API version is set to v3, so you might want to check what version it is set to using this version command before starting to run the etcd commands. So to change etcd to work with the API version 3, either set the environment variable called etcd_API to 3 for each command, so right before you run the command, or you can export it as an environment variable for the entire session using the export command. So that way you don't have to add it before each time the command is run. Now also note that with v3, version is now a command and not an option as it was with v2. So in v2, you had to run -- version, and now, so that was an option, and now it's a command, so you just run version. Now running etcd command now lists the command in the API version 3. So with version 3, now the command to set a value is etcd put, and the command to get a value is etcd cuddle get. And there are many other changes as well in a number of other commands, but that's kind of a high level on how etcd works and etcd cuddle works. All right, so that's all for now. In a later video, we will explore how to set up etcd in an HA environment and how it works with Kubernetes. So thanks for watching, and I'll see you in the next one.
Hello and welcome to this lecture. In the previous lecture, we discussed the basics of etcd. In this lecture, we will talk about etcd's role in Kubernetes. The etcd data store stores information regarding the cluster, such as the nodes, pods, configs, secrets, accounts, roles, role bindings, and others. Every information you see when you run the kubectl get command is from the etcd server. Every change you make to your cluster, such as adding additional nodes, deploying pods, or replica sets, are updated in the etcd server. Only once it is updated in the etcd server is the change considered to be complete. Depending on how you set up your cluster, etcd is deployed differently. Throughout this section, we discuss about two types of Kubernetes deployments. One deployed from scratch, and other using the kubeadm tool. The practice test environments are deployed using the kubeadm tool, and later in this course, when we set up a cluster, we set it up from scratch. So it's good to know the difference between the two methods. If you set up your cluster from scratch, then you deploy etcd by downloading the etcd binaries yourself, installing the binaries and configuring etcd as a service in your master node yourself. There are many options passed into the service. A number of them relate to certificates. We will learn more about these certificates, how to create them, and how to configure them later in this course. We have a whole section on TLS certificates. The others are about configuring etcd as a cluster. We will look at those options when we set up high availability in Kubernetes. The only option to note for now is the advertised client URL. This is the address on which etcd listens. It happens to be on the IP of the server and on port 2379, which is the default port on which etcd listens. This is the URL that should be configured on the kubeAPI server when it tries to reach the etcd server. If you set up your cluster using kubeadm, then kubeadm deploys the etcd server for you as a pod in the kube system namespace. You can explore the etcd database using the etcd control utility within this pod. To list all keys stored by Kubernetes, run the etcd control get command like this. Kubernetes stores data in a specific directory structure. The root directory is a registry, and under that you have the various Kubernetes constructs such as minions or nodes, pods, replica sets, deployments, etc. In a high availability environment, you will have multiple master nodes in your cluster. Then you will have multiple etcd instances spread across the master nodes. In that case, make sure that the etcd instances know about each other by setting the right parameter in the etcd service configuration. The initial cluster option is where you must specify the different instances of the etcd service. We talk about high availability in much more detail later in this course, but I thought it's worthwhile to point it out here. Well, that's it for this lecture, and I will see you in the next. Hello and welcome to this lecture. In this lecture, we will talk about the Kube API server in Kubernetes. Earlier, we discussed that the Kube API server is the primary management component in Kubernetes. When you run a kube control command, the kube control utility is in fact reaching to the Kube API server. The Kube API server first authenticates the request and validates it. It then retrieves the data from the etcd cluster and responds back with the requested information. You don't really need to use the kube control command line. Instead, you could also invoke the APIs directly by sending a post request like this. Let's look at an example of creating a pod. When you do that, as before, the request is authenticated first and then validated. In this case, the API server creates a pod object without assigning it to a node, updates the information in the etcd server, updates the user that the pod has been created. The scheduler continuously monitors the API server and realizes that there is a new pod with no node assigned. The scheduler identifies the right node to place the new pod on and communicates that back to the Kube API server. The API server then updates the information in the etcd cluster. The API server then passes that information to the kubelet in the appropriate worker node. The kubelet then creates the pod on the node and instructs the container runtime engine to deploy the application image. Once done, the kubelet updates the status back to the API server, and the API server then updates the data back in the etcd cluster. A similar pattern is followed every time a change is requested. The Kube API server is at the center of all the different tasks that needs to be performed to make a change in the cluster. To summarize, the Kube API server is responsible for authenticating and validating requests, retrieving and updating data in the etcd data store. In fact, Kube API server is the only component that interacts directly with the etcd data store. The other components such as the scheduler, kube controller manager, and kubelet uses the API server to perform updates in the cluster in their respective areas. If you bootstrapped your cluster using kubeadmin tool, then you don't need to know this. But if you are setting up the hard way, then the Kube API server is available as a binary in the Kubernetes release page. Download it and configure it to run as a service on your Kubernetes master node. The Kube API server is run with a lot of parameters, as you can see here. Throughout this section, we're going to take a peek at how to install and configure these individual components of the Kubernetes architecture. You don't have to understand all of the options right now, but I think having a high-level understanding on some of these now will make it easier later when we configure the whole cluster and all of its components from scratch. The Kubernetes architecture consists of a lot of different components working with each other, talking to each other in many different ways. So they all need to know where the other components are. There are different modes of authentication, authorization, encryption, and security. And that's why you have so many options. When we go through the relevant section in the course, we will pull up this file and look at the relevant options. For now, we will look at a few important ones. A lot of them are certificates that are used to secure the connectivity between different components. We look at these certificates in more detail when we go through the SSL TLS certificates lecture later in this course. There is a whole section just for it, so we will get rid of them for now. But just remember, all of the various components we are going to look at in this section will have certificates associated with them. The option etcd servers is where you specify the location of the etcd servers. This is how the Kube API server connects to the etcd servers. So how do you view the Kube API server options in an existing cluster? It depends on how you set up your cluster. If you set it up with the kubeadmin tool, the kubeadmin deploys the Kube API server as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at etc kubernetes manifest folder. In a non-kubeadmin setup, you can inspect the options by viewing the Kube API server service located at etc systemd system kube API server.service. You can also see the running process and the effective options by listing the process on the master node and searching for Kube API server. Well, that's it for this. Hello and welcome to this lecture. In this lecture, we will talk about Kube Controller Manager. As we discussed earlier, the Kube Controller Manager manages various controllers in Kubernetes. A controller is like an office or department within the master ship that have their own set of responsibilities. Such as an office for the ships would be responsible for monitoring and taking necessary actions about the ships whenever a new ship arrives or when a ship leaves or gets destroyed. Another office could be one that manages the containers on the ships. They take care of containers that are damaged or fall off ships. So these offices are, number one, continuously on the lookout for the status of the ships, and two, takes necessary actions to remediate the situation. In the Kubernetes terms, a controller is a process that continuously monitors the state of various components within the system and works towards bringing the whole system to the desired functioning state. For example, the node controller is responsible for monitoring the status of the nodes and taking necessary actions to keep the applications running. It does that through the Kube API server. The node controller checks the status of the nodes every 5 seconds. That way, the node controller can monitor the health of the nodes. If it stops receiving heartbeat from a node, the node is marked as unreachable, but it waits for 40 seconds before marking it unreachable. After a node is marked unreachable, it gives it 5 minutes to come back up. If it doesn't, it removes the pods assigned to that node and provisions them on the healthy ones if the pods are part of a replica set. The next controller is the replication controller. It is responsible for monitoring the status of replica sets and ensuring that the desired number of pods are available at all times within the set. If a pod dies, it creates another one. Now, those were just 2 examples of controllers. There are many more such controllers available within Kubernetes. Whatever concepts we have seen so far in Kubernetes, such as deployment, services, namespaces, or persistent volumes, and whatever intelligence is built into these constructs, it is implemented through these various controllers. As you can imagine, this is kind of the brain behind a lot of things in Kubernetes. Now, how do you see these controllers and where are they located in your cluster? They're all packaged into a single process known as the Kubernetes Controller Manager. When you install the Kubernetes Controller Manager, the different controllers get installed as well. So how do you install and view the Kubernetes Controller Manager? Download the Kube Controller Manager from the Kubernetes release page, extract it, and run it as a service. When you run it, as you can see, there are a list of options provided. This is where you provide additional options to customize your controller. Remember, some of the default settings for node controller we discussed earlier, such as the node monitor period, the grace period, and the eviction timeout, these go in here as options. There is an additional option called controllers that you can use to specify which controllers to enable. By default, all of them are enabled, but you can choose to enable a select few. So in case any of your controllers don't seem to work or exist, this would be a good starting point to look at. So how do you view the Kube Controller Manager server options? Again, it depends on how you set up your cluster. If you set it up with the kubeadmin tool, kubeadmin deploys the Kube Controller Manager as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at etc Kubernetes manifest folder. In a non-kubeadmin setup, you can inspect the options by viewing the Kube Controller Manager service located at the services directory. You can also see the running process and the effective options by listing the process on the master node and searching for Kube Controller Manager. Well, that's it for this lecture, and I will see you in the next. Hello and welcome to this lecture. In this lecture, we will talk about Kube Scheduler. Earlier, we discussed that the Kubernetes scheduler is responsible for scheduling pods on nodes. Now, don't let the graphic mislead you. Remember, the scheduler is only responsible for deciding which pod goes on which node. It doesn't actually place the pod on the nodes. That's the job of the kubelet. The kubelet, or the captain on the ship, is who creates the pod on the ships. The scheduler only decides which pod goes where. Let's look at how the scheduler does that in a bit more detail. First of all, Why do you need a scheduler? When there are many ships and many containers, you want to make sure that the right container ends up on the right ship. For example, there could be different sizes of ships and containers. You want to make sure the ship has sufficient capacity to accommodate those containers. Different ships may be going to different destinations. You want to make sure your containers are placed on the right ships so they end up in the right destination. In Kubernetes, the scheduler decides which nodes the pods are placed on depending on certain criteria. You may have pods with different resource requirements. You can have nodes in the cluster dedicated to certain applications. So how does the scheduler assign these pods? The scheduler looks at each pod and tries to find the best node for it. For example, let's take one of these pods, the big blue one. It has a set of CPU and memory requirements. The scheduler goes through two phases to identify the best node for the pod. In the first phase, the scheduler tries to filter out the nodes that do not fit the profile for this pod. For example, the nodes that do not have sufficient CPU and memory resources requested by the pod. So the first two small nodes are filtered out. So we are now left with the two nodes on which the pod can be placed. Now, how does the scheduler pick one from the two? The scheduler ranks the nodes to identify the best fit for the pod. It uses a priority function to assign a score to the nodes on a scale of 0 to 10. For example, the scheduler calculates the amount of resources that would be free on the nodes after placing the pod on them. In this case, the one on the right would have 6 CPUs free if the pod was placed on it, which is 4 more than the other one. So it gets a better rank, and so it wins. So that's how a scheduler works at a high level, and of course, these can be customized and you can write your own scheduler as well. There are many more topics to look at, such as resource requirements, limits, taints and tolerations, node selectors, affinity rules, etc., which is why we have an entire section dedicated to scheduling coming up in this course, where we will discuss each of these in much more detail. For now, we will continue to focus on the scheduler as a process at a high level. So how do you install the kube scheduler? Download the kube scheduler binary from the Kubernetes release page, extract it, and run it as a service. When you run it as a service, you specify the scheduler configuration file. So how do you view the kube scheduler server options? Again, if you set it up with the kube-adm tool, the kube-adm tool deploys the kube scheduler as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at etc Kubernetes manifest folder. You can also see the running process and the effective options by listing the process on the master node and searching for kube scheduler. Well, that's it for this lecture. I will see you in the next.